So using the concept of the conditional expectation and the conditional variance as two types of the special random variable, let's apply the new concept into another important applications, that is the random number of sum of random variable. Okay, so here's the situation. Suppose that I visit some number of stores, but I'm not sure about how many stores that I am to visit. The number of stores that I have to visit, that is a random. It's here in this case n. Okay, it's not something like, okay, I have to visit like 10 stores. I don't know. It can be a 10, it can be a 20. Let's suppose that the xi is the money that I spend in store I, and that is independent of other like xj, and also the number of stores n. And let's assume that the xi's are identically distributed with mean mu. Okay, so I'm going to spend on average mu money on each store. I'm interested in the total money that I will spend. At y is equal to the x1 plus x2 plus to the xn. And what I'm interested in is the expectation of y and variance of x. This problem becomes very easy if the number of stores that I have to visit is fixed as a constant. Because these xi's are independent, expectation of y is equal to the n expectation of anything, because it's identically distributed. And also the variance of y is equal to the what? N variance of each xi. Because again, it's an independent. The linearity can be satisfied from the independent. So again, the number of stores are fixed, and the problem is easy, but the problem is n is random. So the question is, how do the result change if we consider the random number of stores? Okay, let's compute the expectation. Since there are two random part, y and n, so whenever we have some two random variables and then we need to compute the expectation, we need to think about law of iterated expectations. So that is equal to from the law of iterated expectation of y given n. Okay, and if the n is given, then the expectation of y is that the n multiplied by expectation of xi, because n is given. All right, and the n and xi's are independent of each other, so it can be decomposed and factorized into the expectation of n and expectation xi, and that is equal to the mu multiplied by the expectation of n. So it's not that different from our intuition. Even if the n is random, then the answer should be mu multiplied by expectation of n. Okay, that's good because it follows our intuition. What about the variance? So the variance, we're going to use the LTV. Let's first compute the variance of expectation of y given n. Now n is given, then what is expectation of y, and that is n mu. And that is equal to the mu is a constant, and now mu square variance of n. Okay, that's this part. Now we're going to compute this part. In order to compute that, let's first compute this part. Variance of y is given n. So if the n is given, then what is the variance of y? That is n multiplied by the variance of xi, if n is given. Now, but n is random, so let's compute the expectation of the variance of y given n. And that is the expectation of this guy. Variance xi is a constant, and so constant multiplied by the n, so the constants comes out from the equation, and expectation of n multiplied by the variance of xi. So we get this, and this should be added together. So we get this formula. So again, if the n is fixed, what will be the roughly this part, right? This is fixed as n, but we have another part of the variability of n. That's what we need to consider additionally. Thank you.